Hello everyone, this is the part 2 of free particle in 1D infinite potential well problem. In our previous video we have estimated the energy values for the particle and we have found that E is proportional to n square, where n is one integer and the energy values are quantized. Now n can have value 1, 2, 3, 4, n can't be 0, the reason we have discussed in our previous video. Now if I plot this, for n equal to 1 we have the ground state and the energy value is pi square h cut square by 2 ml square. For n equal to 2 we have first excess state and the value of the energy is 4 pi square h cut square by 2 ml square. For n equal to 3 we have the second excess state and the energy values are 9 pi square h cut square by 2 ml square and so on. One important thing to note that the separation between the energy level decreases with increasing n value. So these energy levels are not equispaced and all the energy levels are discrete and quantized. Now let's estimate the energy difference between the first excited level, that is for n equal to 2, and the ground state energy, that is for n equal to 1, and this value is 3 pi square h cut square by 2 ml square. So delta E21 is inversely proportional to L square. So in the above equation, if L decreases, so if L decreases, delta E21 increases. So L decreases means the length of the box decreases. The particle gets more confined. So if the particle gets more confined, delta E21, that is the separation between the energy level, increases. That means the separation, the energy gap between these two energy levels increases and the energy levels becomes far apart. Further, now in this problem the particle is free over a length L. Now if I consider one completely free particle, we should have L tending to infinity, and it is not confined anywhere, it is free everywhere. So L must be infinity for one free particle. Now in the limit L tending to infinity, the above equation, from the above equation we found that delta E21, so if L tending to infinity, delta E21 becomes 0. That is, the separation between the energy levels ceases and the energy levels become continuous, which is the case for free particle. Now this is the wave function. We have estimated the Kn value, but C1 yet to find out. We have used all the boundary condition. We need one more condition to find out the value of C1, and that condition is the condition of normalization. In this integration, the psi square is called the probability density. So this integration tells that we are integrating over whole the space from minus infinity to plus infinity on the probability density. Hence, the integral estimates the total probability of finding the particle, and hence it must be equal to 1. We'll use this condition to find out the value of C1. Now the particle, it is important to note that the particle is only free inside and the wave function has finite value only inside this box, and it is 0 everywhere. That is, that psi is finite only between 0 to L and 0 everywhere. So I can change this integration limit from minus infinity to plus infinity to 0 to L, as everywhere else psi is 0. If I put this value here with Kn this value and I do this integration, I find out that C1 is equal to root 2 by L. So using the normalization condition, we can estimate the value of the normal constant C1. So this is for the ground state. I have put the value of C1 and n equal to 1. So I have this. Now if I put x equal to 0, my wave function becomes 0 because sine 0 is 0. Now if I put x equal to L cancel out, I have sine pi which is also 0. So at x equal to L also, psi 1 equal to 0. That means the wave function is 0 at the edges of the box, at the boundaries. The wave function is 0 for the ground state. Now where the wave function is maximum, for the maximum I should have sine pi x by L is equal to 1. That means that pi x by L is equal to pi by 2. If I simplify, I get x equal to L by 2. So the ground state wave function is maximum at x equal to L by 2. So if I plot this is essentially a sine function. So I have this, where at the edges or at the boundaries the wave function is 0 and it is maximum at x equal to L by 2. Similarly, we can plot the wave function for other excited states. For example, this is for the first excited state, this is for the second excited state. One important to note in this is this arrow position. This arrow position denotes the position of where the wave function is 0 all the time, and these positions are called nodes, as the probability of finding the particle is always 0 here. The wave function is 0, so obviously the probability of finding the particle psi square is also 0 at this position, and these positions are called nodes. The number of nodes for the ground state is 0, for the first excited state is 1, for the second excited state is 2, and it increases with increasing n values. Further, we have seen that the probability of finding the particle between 0 to L, which is 1. Now if I was asked that what is the probability of finding the particle between 0 to L by 2 for, say, the ground state wave function, then I have to do this integration from 0 to L by 2, and if you do this integration putting n equal to 1, you should get a value of half. That's all. Thank you.